comes back to what degradation mechanism you're trying to understand and to follow in that sense. So let's say you were looking to understand the impact of increased fluoride in the processed water. You may decide to operate at standard current densities and just have a large amount of fluoride in there, put ppm quantities in, for instance, which we've done. And that way you're kind of isolating those differences. Now, one of the problems, obviously, with doing AST development is it could be really easy to go to a regime where you're accelerating things so much that you're actually taking things away from the natural mechanisms that really happen, and you're putting them into a different degradation regime. So that's something to be very, very mindful of, different failure regime. But what sort of things that we've done would be to run at high current densities. Very straightforward. Now you do need a cell design that allows you to do that. But we've run at high current densities. We've done lots of start-stops, which again is quite an interesting feature to look at how things perform over that sort of cycle. We've run at different temperatures. You can see where I demonstrated earlier, we've run a couple of different temperatures here, and we've done that a wider temperature range ex situ. And other things that you can look at, different pressure, differential pressures, which I know some of our customers have looked at as well. Because that gives different membranes on a different position, different compression when you have that differential pressure. So it's all about what's the mechanism, which the particular failure mode you're trying to accelerate, and how do you then do that without really pushing it into a boundary where it's just not relevant. And that's unfortunately a little bit of an empirical approach, because then you have to characterize the materials that you've tested under that environment to see if you still get the same failure mode that you saw when you were trying that led you to that being a concern. So a little bit of feedback ultimately needs to be developed to really make sure you have the right accelerated stress test. Again, very, very similar things for all electrochemical, if not all technology spaces. You can run a machine really, really hard, but if it's never, and then it fails, but if it was never intended to run in that environment in that way, then what are you testing? So you have to be really, really careful. But things like fluoride, high current densities, start-stop cycles are sort of typical things we'll be looking at when we're doing ASTs.
Thanks, David. And Gurjant, from the AEM point of view, are things very much the same?
Things are the same, but I think I might have some personal opinions on that. Even though we say that we're gonna do stress tests, increase in current densities, that may not always mean that system in the field is failing because of that, right? I mean, I see that we have stress tests as this, so that stress testing, for example, let's say at 4 amps per centimeter square, when the system is running at 1 amps per centimeter square, in the field, the failure may not lead back to the same problem, right? It's again, it's a very tricky question, as at the same time. But yes, we do in our labs, for example, we do tests at high ampacity, excess number of shutdowns, on-offs. Then we also do kind of different pressures, different temperatures, high temperatures. I think it's actually is one of the main things, or one of the key testing parameter is test your system at high temperature. So we do all these things, but again, it's gonna add something that that may not always mean that the failure in the field is because of the these reasons or these parameters.